Okay, let's unpack this. Imagine looking at a sea anemone, all flowy and kind of alien looking,
Uh-huh.
and then finding out it might actually hold a key, like an ancient blueprint for your body.
It sounds pretty wild, right? But that's sort of what we're digging into today.
Exactly. We're doing a deep dive into this really surprising scientific finding. It could genuinely shake up how we think about the timeline of evolution.
Yeah, it's about how these creatures, which seem so different from us, can tell us deep secrets about our own biology.
So let's start with the basics. The bilaterian body plan. Most listeners probably know this intuitively.
Yeah,
It's us.
right. Bilaterian just means symmetrical along one plane. Think front, back, left, right.
Like worms, whales, ants. Even you listening, you're a bilaterian.
And the common alternative, the one we often contrast it with, is radial symmetry.
Like a jellyfish.
Exactly like a jellyfish.
Yeah.
Or a coral. They're organized around a central point, like spokes on a wheel, no clear front or back.
And most of those animals, jellyfish, corals, sea anemones, they belong to that group, the cnidarians. They usually have that radial plane.
Usually, yes. That's the general rule.
Okay, so you've got these two main plans. Bilateral, like us. Radial, like jellyfish. Seems neat.
Hmm.
But nature loves throwing curveballs, doesn't it? And that brings us to this specific sea anemone.
Ah, yes, the starlit sea anemone, Nematostella vectensis.
What's the deal with that one? It's a cnidarian, so it should be radial, right?
Well, that's the fascinating part. Despite being a cnidarian, Nematostella actually shows pretty clear signs of bilateral symmetry, not radial.
Whoa, okay, so that muddies the waters a bit.
It really does. It immediately makes researchers ask, hang on, when did this bilateral plan actually evolve? Was it just once or multiple times?
Right, and to figure that out, you have to look at how bodies are actually built, the molecular tools.
Exactly. And a key player here is a protein called bone morphogenetic protein, BMP.
PMP, okay, I've heard of that. It's crucial for development in bilaterians, yeah.
Absolutely crucial. It works by creating a gradient, like a concentration slope, across the developing embryo.
So, like, high levels here mean become skin, low levels there mean become nerve tissue, something like that.
Sort of, yeah. It tells cells what they should become based on their location.
Yeah.
It's fundamental to setting up the body axis.
Okay, so BMP is the signal.
But it's not just that BMP is there. It's how it's controlled, how that gradient is established and maintained. That's the sophisticated part.
And this is where the new research comes in, from the University of Vienna.
Precisely. They looked closely at the starlit sea anemone and how it handles BMP.
And what did they find? Does it use BMP differently?
That's the kicker. They found the anemones use the exact same kind of regulatory mechanism for BMP that we see in bilaterians, like frogs, flies.
The same mechanism, huh?
It involves another protein called cordon. Cordon acts like a shuttle.